recording for the academic year 2014-2015. It's been a tough year, but I'm glad it's almost over. Summer's almost here. I bet you all are too. So we were talking about virtual memory some more. I mean, we've spent quite a few lectures talking about this by now. And remember that this is the 32-bit address layout for a Linux process, roughly. One of the things that they've started doing to make it a little bit more secure is that they shuffle these a little bit. Just a little bit, because people generally expect that it's going to be laid out this way. Like, just as a little aside, the test program that I gave you guys for assignment 8 is like matrix multiplication, and I thought, you know what? It's totally feasible that you could completely mess up memory in such a way that you don't realize it and everything looks fine by the end of the program running. So I thought what I'll do is I'll allocate matrices using the virtual memory space, and then I'll allocate mirrors of them using malloc, and that way I can compare them along the way and see if everything's jacked up at the end or not. So hopefully that'll help some people. I don't know that it'll be a very common issue that people will run into. But the thing is like you look at this diagram and you're like, okay, where does stuff get laid out? And you see where the heap is, so it's going to start somewhere like 804, 8000 is program text. So if we don't have a whole bunch of code and we don't have a whole bunch of global data, then maybe we're going to be pretty close to that, and the heap is just going to grow upward from there. And then at some point we have shared library memory, so you can see where that is. And then we have the user stack above that. And then above a certain point we have kernel. Well, the problem that I ran into when I was trying to get the virtual memory lab working is that I asked mmap to give me an address. Hey, just pick an address for me. And it did. And then I started mallocing stuff, and it turned out that mmap and malloc gave me overlapping addresses. So that when I wrote to one matrix, it would corrupt another matrix. And it took me hours to debug. It was so frustrating. And so what I did was I was just like, all right, I'm just going to pretend like the heap is never going to be larger than, I don't know what I picked, like 200 megabytes or something like that. And so I just hard-coded an address into mmap so that it would hopefully never collide. Yeah.
So when you use mmap, the address that you put in is the one in the space, or is it the one that you're mapping to?
So the one that you put in is actually a virtual address as far as the process's virtual memory abstraction is concerned. Yeah, it just so happens in assignment 8 that we don't have any physical address to virtual address mapping because we don't have a physical to virtual address translation mechanism that we can use. So they're all the same. The physical address and the virtual address are the same for assignment 8. So yes, it's the actual address. The address you put into mmap would be the start of the page that you actually want to use. And there will be some values at those actual addresses that you're reading and writing. We might need to take this, talk about this after class if it's not entirely clear. But you can see that this layout is, it has to follow a general pattern if everything is going to work properly. And you can generally work within it, but it can be a little bit finicky as well, or risky to try to hard code things at specific addresses. So anyway, I just wanted to mention that. Yeah, so all processes have a similar layout. They all generally start at 804, 8000, more or less. I mean, like I said, they'll do a little bit of adjustment. And the stack generally grows down from a particular maximum value, although, again, they will adjust it just for the sake of security. And also, we talked about how the kernel is able to map some of its code and data in so that we can actually have fast system calls, so we can trap into the kernel faster because it's already there. But the program is not allowed to access it directly. This is also where the context for the process is stored, so that's memory map, its actual page directory structure that we hand to the MMU when we context switch to the process, what else? The virtual memory area descriptors and so forth. So all of that stuff gets stored up there, and the process is not allowed to manipulate it directly, but since it's associated with the process, we might as well put it in its own virtual address space. Okay? So are there any general questions about this? Okay. Yeah, so, and we started talking about these VM area structs, which are kind of neat because what they allow us to do is to provide abstractions or capabilities that are above the actual capabilities of the MMU. And hopefully some of you have already started to see or get a sense of how this actually can be used in Assignment 8, because Assignment 8 has a very limited capability as far as what we can actually control with memory, but we can emulate certain things, and then we can, Linux even emulates more sophisticated things above that, a few of which we will talk about today. But the whole point is that since the hardware isn't necessarily going to always provide the same set of capabilities, we can emulate some things in software, so these VM area structs allow the kernel to keep track of a few additional details. So yeah, like I say, page faults and general protection faults. Okay, few more details. This is sort of the last final piece of the picture, is what Linux does as far as where the data comes from when you memory map a page in the virtual address space of a process. So like I say here, every memory area is associated with some object on disk. So we said that DRAM is going to be a cache for data on the disk. And so basically, since that's the way that we want to construct our operating system, we can keep it really simple and say every page is backed by some source of data on the disk. And so we sort of have a couple of choices, and these are where the data comes from. So like you say, a regular file in the Unix file system, a binary, a shared library, a data file if I'm writing a database and I want to be really fast, or what's called the anonymous file. And you have to use the anonymous file in Assignment 8. Basically, the anonymous file is a file-like thing, so you can read it and you can write to it, although writes are completely ignored. But when you read it, you always get zeros back. It's like the easiest thing to write ever. Okay? I want to read some data. Sure, here's a bunch of zeros. That's what it does. Okay? And so this is really helpful because since they're all presented using the same abstraction, Linux can just say, here's the file that's associated with this page, and it happens to be in the anonymous file, and then when the virtual memory system pages that page in, boom, it's magically full of zeros. Okay. Yeah, so this is what I was saying before. So I want to expand my heap. I want to expand the stack because I'm starting to make calls and I need more virtual pages for the stack. Then when the thing is paged in, it's paged in from the anonymous file so that it's automatically filled with zeros. Now you'll see here this last point that I mentioned here is kind of a subtle point. There's two important stages in a virtual memory page's lifetime. One is when it's loaded, because you have to know where does the initial data come from. And then the other moment is when it's evicted. Where does it go to? Okay? So the initial step is pretty obvious. I want to memory map a file. I want to memory map I just want pages, so give me the anonymous file and they're filled with zeros. The thing is that obviously when a page that was from the anonymous file gets evicted, it can't just go back to the anonymous file because it's a virtual thing, it's a fake thing. And so it goes into a swap file or a swap partition. Okay, so it goes to some swap device. But the same is actually true for regular files. If I page in data from a regular file, and I tell the kernel that I don't want my changes to that page to be visible to anybody else, which you can do, we'll talk about it in a second, then when that thing has to be evicted, it goes to swap, it doesn't go back to the original file. Because if it went back to the original file, everybody would see the changes. So you can see that you have these two important points in time where you have to think about where does the data initially come from, and then when I have to evict a page, where do I save the data? And so there's a couple of configuration details. The reason why I mention this in such detail is because in 124 you have to actually go through and figure all that stuff out. It's actually pretty important for understanding virtual memory, but it is a little bit more of an esoteric thing. It's not really a fundamental detail that you absolutely have to be aware of. Just if you want to understand it really well. Okay, yeah, like I say here, the anonymous file is used when the kernel allocates new virtual pages to a process. Why is it using the anonymous file? Now, I already said that the result is that the page gets filled with zeros. But the thing that I'm getting here is, what was in that page before it was assigned to the process that's now using it? Remember, that virtual page is assigned to a physical page frame. What was in that page frame before the process started using it? Well, hopefully not sensitive business data that gets leaked across processes, or passwords, or passphrases, or private keys, or any number of other things. Basically, the operating system kernel has to make sure that processes can't bleed information between each other by accident. And so that's part of the reason why when new pages are assigned to a process, we always have to ensure that they are either zeroed out or they're taken from some file's contents. Otherwise, we could easily have a situation where one process leaks information accidentally to another process because the operating system sucks. Okay? So you say our process prompts the user for password, another process allocates a virtual page, which goes to the same physical page, so the old page was evicted, but we need to clear out the contents of that page. So that the second, because this is a shared resource, we need to make sure that we don't bleed information back and forth. Okay? This is pretty obvious, right? I don't think anybody's going to really find this shocking and surprising. I never guessed. Okay, so then the next part of this is what I was saying before about, well, when I evict a page, where does it go? Who all gets to see my changes that I make to this thing that I load into virtual memory? And so you have either shared objects or private objects. And like I say, these are just terms, so the memory area that the shared object is mapped into is called a shared area because multiple processes can see that area. And same thing with private objects. You map it into a private area, only one process gets to see it. And so there's a simple example of this is libc. I've been kind of mentioning this all term, that everybody seems to use libc. I mean, it's possible that you don't have to, but most people do. And so what you want to do is load that into memory once, and then map it into the address spaces of multiple processes. Of course, the caveat of this is that now that I have multiple processes' virtual address spaces mapping to the same physical pages, if one process decides to be dumb and change the data in that physical page through their virtual address space, because they're allowed to, then everybody will see the changes. And not only that, but when the page is evicted, that change will get stored back to disk. So this is a pretty big gun that you're handing processes. And so the result of this, or the upshot, is that the kernel needs to be very careful about how it manages permissions to these shared objects. So for example, they may say, yeah, so you're loading libc, and generally it's not a good idea to have programs modifying code. So what I'm going to do is map this shared object into everybody's address spaces, but it's going to be read-only. So that A, you can't jack up libc so that it gets saved back to disk and it's mangled somehow. And everybody else doesn't get affected by you trying to be dumb. Okay? So that's kind of the idea. You can make a shared object and read-only so that everybody can share this. You only have to load the file once, but then nobody's allowed to change it, so it won't affect everybody. Now, private objects are kind of interesting because you should be able to still modify things, but the change shouldn't modify the private object on disk. So we have a couple of approaches, and the really naive approach would be somebody's loading a private object from a file. So what I'm going to do is just make another copy because they're allowed to change it. We don't know that they will change it, just that they might. They haven't changed it yet, but we're going to go ahead and make an extra copy. And so you can see that this kind of becomes really prohibitive if you have this approach in general. So, and it's interesting because some operating systems actually allow you to load shared libraries and then modify them, but you can do it as a private object so that your changes don't become visible to everybody else. It's actually something kind of unusual that you can do. One of the CS24 TAs did a project way back when, I think he was a freshman, where he would load Windows libraries and he would load them as private objects, so they were still shared across the operating system, but he would change them, and the changes would not become visible to everybody else because of this technique that we're about to talk about. But sometimes you can do that kind of thing. He was building a sandbox so that you could prevent certain system calls from being executed successfully. So he had a way of just sort of sandboxing an application. You download an app off the internet, you don't know if it's trustworthy, and so you can run it in the sandbox and it would intercept system calls and make sure that you actually approved of those calls occurred. So it was kind of a really neat thing, and he relied very heavily on these virtual memory techniques. Okay, so the technique we're going to talk about is copy on write. Very powerful. So private objects, instead of loading them many, many times, once for every process that wants to have a private object in memory, what we can do instead is load it once. And we set up this thing called copy on write so that if the process decides to modify it, then we only make a copy of the part of it that gets modified. Okay, so like I say here, the objects pages get set to read-only, and that is at the MMU level. So what happens? The MMU has them as read-only, so if I try to write to that area, I get a fault, just like you guys hopefully are going to see in assignment 8. But the VM area structs don't just say it's read-only, they actually say it's private copy on write. So the VM area struct is representing a higher level detail here. So we have this simple example. We have two processes, process A and process B. They both happen to load an object into memory as private copy on write or private cow, which is a little weird. But anyway, so we load this thing into physical memory once, and you can see that it's mapped into each process's virtual address space. Doesn't have to be at the same address. That's one of the fun nuances and sort of wrinkles of dealing with shared memory, that you can have them appear at different locations in the virtual address space, which makes shared library linking and things like that a little bit challenging, but very cool. Cool stuff to look into. Okay, but anyway, the object is loaded once, and they both have a VM area struct for that region saying, here's the file it's from, it's private copy on write, and both of them have a page table saying, this region is read-only, so that if any memory access to that region is a write, then it'll cause a fault. Okay, so just like I was saying, one process decides to write, so it's going to generate a fault. And the kernel basically steps in and does something very clever. It sees the faulting address. We can get that from the hardware. There's a special register in the IA32 processor that holds the faulting address, so you can just pull it out and now figure out what to do about it. So you map it to the page that it came from, and basically you look in the VM area structs and you're like, oh, that's private copy on write. So it duplicates that page and then remaps it and says, hey, MMU, it's okay if writes occur to this. Because the OS knows, well, if writes occur to this, the process is the only thing that's going to see it. So create a new page, copy the data from the old page to the new page, and replace the old page in the page table with the new page so that we update the mapping. Okay. So we have it right here, just as a simple example. The kernel gets a GPF, general protection fault. Now remember, this is not exposed to the process at all. This is all handled entirely by the kernel. So again, the kernel is an intermediary between the hardware and the application, giving it this really clever abstraction that allows us to have very efficient memory use. And so the page is flagged private copy on write, so the kernel does the private copy on write steps. Sets aside another page for the process, copies the data into it, updates the mapping, and says, hey, this part is now writable. Okay. And like I say here, the copied page is marked read-write, not just read-only, because we now have a copy. And so then the kernel returns from the fault handler and tries the application tries the instruction again, and this time it succeeds. And the process A is the only process that actually sees the changes that are made to that page. Okay? So it's very straightforward. Are there any questions? I think this is just really freaking cool. Now, one little detail about this is that the VM area struct for this section of memory in process A will still say private copy on write for the entire thing. Okay? It just so happens that the page table entry is going to say something else, and that's what the MMU looks at. The MMU doesn't care about VM area struct. It only cares about what the page table says. Okay? So we can have these two things, like sort of the private copy on write is an umbrella, and it sort of covers multiple possible states that page table entries might be in. Okay, so enough about that. This is basically exactly how fork works. When you have a process and it decides to call fork, the kernel doesn't actually copy all of the contents of the process. There's like just a few things that need to be set up. If we have two processes now, well, we need to have a new kernel stack space because the new process will need its context stored. We have process ID, parent process ID, but a lot of other details are just duplicated. And the entire address space of the process is duplicated as well. Okay? So we can actually do this with private copy on write. And it's kind of funny because I think I mentioned this before that back in the 60s and the 70s when people were actually starting to do this stuff, forking a process was really expensive because we actually had to copy everything. And memory was really slow. I was actually just looking on eBay. I don't know why I get excited about this stuff, but the old memory cores. If anybody wants to see an old core memory from like the late 60s, you can come by my office and I'll show you a little plane that would hold 4K bits of data. And it would be like maybe a half second to access data. And so what they would do is they'd stack up a whole bunch of these planes into like a brick. And so you'd have this big brick that you could read at a decent rate. I mean, maybe I don't know, maybe if you were really good, you'd get down to a tenth of a second or something like that. They were really happy with that. And it might hold 32 kilobytes, this big, like, brick of memory core. Okay? And so you can see why forking would be really slow because now we're copying and the device is also incredibly slow. Okay? And it would be slow if we did it on modern hardware as well. So thankfully, we can use this copy on write technique to fork a parent to a child, and that way, as the child and parent start to deviate in their state and their behavior, well, we can just private copy on write the pages that change. Okay, so we duplicate all the process-specific data structures, page tables and MM structs. Obviously, those things we need 2 copies of. So we can go ahead and duplicate that. All of the pages in both processes are flagged as read-only because we need to be able to do the private copy on write thing. Okay? So that's all the stuff like below C000, blah, 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 blah. Everything that's in user space. If any process, parent or child, writes to a particular page, like they call malloc, or they open a new file, or increment a variable, or whatever, then you get a fault, and that page is duplicated using the private copy on write technique. And so you have this thing where the parent and child, even though they share as much as possible that hasn't changed, they still have this illusion that they actually have completely independent address spaces and completely different memory regions. That way the code is only loaded once. Anything that doesn't change is only copied once. So it's a very, very efficient technique for forking processes. Okay? Make sense? Cool. Thankfully, we never have to implement this because it would actually be really complicated. There's a lot of wrinkles when you do this stuff. Okay, exec_ve. Like I say here, loads and runs a new program in the process context. So we basically have to go through all the VM area structs and the memory map, clear all those things out. So this is just what I was describing before. We need to just go through there. Obviously, there may be pages that are dirty. And when they're going to be evicted, they need to be written back. So cleaning up the VM area structs can actually take a little bit of time because we need to make sure that anything that was changed actually gets persisted properly. Then we go ahead and set up the memory areas. So we have the binary file. There's certain things. We haven't really talked about this, which is too bad. I would love to talk about this. If we had a compiler class, then we would talk about it a lot. .text, the program text, we've all done like .text at the top of our files. .data is initialized data, so that's values you put into your global variables or static local variables. Uninitialized data is variables that you don't specify an initial value for that are global variables or variables that you set to be 0. They get mapped into BSS. Okay, so the initialized data and the program text come from the file. So clearly we set up memory mappings to those parts of the file. And so then when they're referenced, we talked about this before, then the kernel will start swapping them in automatically. Okay? And like I say here, you can either mark that just private read only if it's something you should never be allowed to change. Things like constants are a really good example of this as well, but program text definitely. But if it's something like initialized data, well, if it's mapped from the file and I change it, and then the page gets evicted, that would modify the original program file. So I don't want that. I just mark it as private copy on write. And then as the data changes, then it will go into swap as opposed to going into my program file. Okay, so let's see. An uninitialized data, that's not in the binary file because, hey, it's uninitialized. So we map that stuff to the anonymous file. Okay. What you may have noticed, I don't know if you ever noticed that, like, when you run your program, we always talk about in CS11, like the C track and the C++ track, and you see it a lot in here, that it's like, oh, these values aren't initialized. It's whatever crap was already in that memory when you start running the program. Well, except that you notice that some of these values actually do seem to be zeros, which is kind of weird. Well, the reason why is because they're actually mapped against the anonymous file. It's not like when you start your program, you've just got a whole bunch of random garbage in memory. Most of it's mapped from the anonymous file, so it's going to be zeros. And what happens is, as your program runs and the stack grows down, and then it grows back up, and then it grows back down, or you have memory heap allocation, so you allocate, use it, and then it's freed, and then you allocate other stuff. As your program runs, it leaves a bunch of garbage in memory, and that's the garbage you sometimes see in variables that are uninitialized. But at the very beginning, everything starts out as 0. And so you can kind of count on that. That's the whole kind of idea behind mapping uninitialized variables or variables that are initialized to 0 into the BSS segment, because they're taken from the anonymous file, so you can guarantee they'll be zeros. Okay, any questions about that? A little bit subtle. I don't know. It's, like I said, it starts to get into some of the more esoteric details here. Okay, user stack and heap to the anonymous file as well. Again, if you've looked at mmap, you may have noticed that there's some special stuff for the stack because the stack needs to be able to grow down. The heap grows up. Most of our stuff grows up, but the stack is special that grows down. And so there's actually special things that you do in the kernel to keep track of that so that you can keep track of, how much should I allow the stack to grow and consider it valid. Like, if it goes into the next page, that's probably okay. If it's like 40 pages down from the top of the stack, it's probably a bug. And so the kernel will prevent certain things like that going on. So it has to keep track of the fact that the stack is growing down as opposed to growing up. Okay, shared memory areas. So if we have any shared libraries, this is like the 4000 section. Then we map shared libraries into the processes virtual address space. There's a whole thing called dynamic linking. Some of you may have heard of dynamic linking. Really cool mechanism. Because like I was saying, the operating system kernel doesn't know what shared libraries are required across the board. When it opens up the file, then it knows what shared libraries are necessary. And so it figures out what addresses to load them at. And so you might have the same shared library at different addresses in different process address spaces. So you have to write the code in a special way to make sure that it actually is position independent. I don't know if any of you have seen this term PIC before, and I don't mean the microcontroller, but in specifically in compiling and linking, it means position independent code. You can tell the compiler to generate code that can be loaded at any address, and this is essential for shared libraries. So that's dynamic linking. And yeah, so in this case, shared libraries would be shared read-only. If you have other things like data files that maybe are open, then they may be shared and, read-write and so forth. Okay? Questions? That is about the most detail that we'll go into with execve. Let's see, yeah, so we set up the program counter to the entry point, which is this little wrapper that sets up the stack and sets up the heap and calls your main. That's basically all the entry point does. Okay? And so then as it runs, the virtual memory system just automatically starts loading in pages as needed. Okay? So that's basically the gist of how all this stuff hangs together. Any questions about virtual memory at this point? Yes?
When uninitialized data is initialized, does it say in that block? Like when you assign a value to it?
I'm trying to understand the question. Can you be a little bit more specific?
Like where I guess a variable is stored. I don't know how that works.
So the address, are you saying for uninitialized data?
Yeah.
Specifically. So what will happen is the compiler will say, this is the address of this variable, and I know it's not initialized.
Okay. And then when it is initialized, that's just put in there. Is that moved around?
Well, so the thing is that the how can I describe this? So basically, what the compiler, and this is really a job of the linker particularly. It will figure out what is the extent of the program text. So the program text, let's say, starts at 804.8000 and is a certain size. So it will end at a page boundary, and then above that will be initialized data, which it again loads from the data file. But that will also be rounded up to a page boundary, and then you'll have this point where it'll be uninitialized variables. The variables all live within a specific address range. So if you have some counter that is a global variable and it's uninitialized, the compiler will say, or I should say again, the linker specifically is the thing that does it. The linker says, this is the address where that counter is going to live. And everywhere in the program that refers to that counter, that is the address that it actually uses. It encodes that address everywhere in the program. It just so happens that when the program is loaded, the operating system maps that page that the counter lives in to the anonymous file so that it's initialized to zeros. Does that answer the question?
Yeah, and I don't know, does that mean globals will never be like garbaged up by mallocs and stack?
Does that mean that they will never be garbaged up? Given correct program behavior, they should never be garbaged up. Yeah, they should actually be zeros. That is if you have this model. Unix has this model. BSS has been around for freaking ever. It stands for block segment start, and I don't even remember why it's called that, but it's some anachronistic reason along the lines of a.out. Like, why when you compile something does it generate a file a.out? It's like, okay. It's historical reasons that are now kind of out of date. So, yes, if you have a correctly operating program and correctly operating libraries, and you're on an operating system that provides that abstraction, which Unix systems do, then, yeah, you can basically count on those things being zero. The compiler does. Because if you initialize it to zero, it doesn't put it in initialized data. It actually puts it in uninitialized data. So yeah, the compiler's relying on that, for sure. Okay, anything else? Any other questions? Alrighty, let me see. I think I have like one more slide about virtual memory. Like I say here, there's many different features. We've talked about all of them pretty much to death now, at least as far as we care about in CS24. So address space isolation, very powerful. This is one of the few fundamental things that have to be provided by an operating system kernel. There's basically two things, and they both center around process abstraction. I need to be able to time slice or multitask the CPU, and I need to be able to provide isolated address spaces. Everything else is kind of extra, which is why people who write microkernels are like, they make a kernel that's like 6,000 lines of code, and all it does is provide time slicing or time sharing on the CPU and address space isolation. And everything else is provided outside of the kernel, and it turns out to be kind of slow. Okay, but we'll talk about that in 124. But anyway, fast context switches and process forking using our various fancy pants techniques, copy on write and so forth. Loading of programs and libraries into main memory. Remember, we can just set up the mappings, and then the virtual memory system just automatically starts loading them in. Efficient memory use, sharing common data across many processes. That's extremely important and powerful. In fact, it's so common. Like when I was an undergrad and we would install Linux from a stack of 3.5-inch floppy disks that was like inches tall. We didn't really use shared libraries very much. It wasn't as common a technique. We would use statically linked libraries, and so all of our binaries were slightly larger. But now it's like so common to use shared libraries. In fact, on the Mac, they only support shared libraries. You can statically link stuff if you really force it, but in general, it really, really strongly prefers shared libraries. And so it's kind of interesting this technique has become so ubiquitous. All right, so that's all I had to say about that. Are there any questions about virtual memory? I already asked that once. But. Okay, so the last 20 minutes, 15 minutes. Let me see what time it is. Yeah, 11:40. So what we'll do is we're going to spend a little bit of time talking about one little topic that I probably need to move forward in the sequence because Everybody has solid-state drives now. Not everybody. Who here has solid-state drive in one computer that they actually utilize? Okay, so there's a few people that don't, or you just don't want to put your hands up, and that's fine. But very common to have solid-state drives. If you don't have one yet, almost certain that you'll have one in your next system that you use. So I just want to mention this specific thing, because you've probably heard of trim, right? Who's heard of trim? Some of you? Okay, trim is a thing, and you want to turn it on. Those are like the important things that people sort of walk around in their heads about trim. So I wanted to spend a little bit of time talking about solid-state drives, because people think, oh, solid-state drives, they're way faster than magnetic disks. I don't have to think about anything else. They're just awesome. Well, they're kind of awesome, but they have some drawbacks as well. And the specific thing that I want to talk about is deletion, because that's where solid-state drives start to manifest some of the challenges that you can run into with them. So like I say here, file systems will separate directory information and file contents. I already kind of talked about this a little bit, that if process A opens a file and then process B deletes the file while A is still running, what happens? And on Unix systems, what it does is it removes the directory entry. It's called unlinking it. And then when process A finally terminates, then the actual file's contents are collected. So you have this separation between directory entries, which in this case are boxes, and the actual file contents themselves, which are the circles. And maybe you've made symbolic links, but there's also hard links. Hard links are actual directory entries that point to file data on disk. Symbolic links are a file whose contents point to another file. So it's a slightly different way of doing it. Windows really prefers symbolic links. On Linux, it's very easy to create either one using the ln function, ln program. Okay. You can make hard links on Windows as well, but it's pretty uncommon. Okay, so what this means is that when you delete a file, you have two operations that have to occur. You remove the directory entry, and you look at how many directory entries now refer to the file. And if no more directory entries refer to the file, then you know that the space can be reclaimed. Okay? And I talk about marking the file space as available. We go into this in a lot more detail in the OS class. But typically, for each device or each partition, you'll have some map that says, these are the parts of the device that are available for storage. We call it a free space bitmap or some kind of free list that describes what space is actually available. The consequence of this is that we want it to be as fast as possible because disks are slow. And so we generally only touch the directory entry, and we only touch the bookkeeping stuff that says this space is now available. We don't touch the file's data at all. We don't go and write over it so that we're doing a secure delete or anything. I mean, some of you may do that kind of stuff. People certainly do, where it sort of overwrites the data multiple times to make sure that it actually gets clobbered before actually marking it as deleted. So, but what you see is that the OS just stops using those sectors. It just says, you know what, I'm not using them now. The free space bitmap will say this stuff is now available for use, but the data is still there somewhere. Now this becomes more challenging with solid-state drives because of the way that they actually interact with the flash memory inside the device. So like I say here, they're block devices, reads and writes are a fixed size. But you're only allowed, it's like this weird set of rules like you'd see on a ditch day stack or something. You're only allowed to write to a block that's empty. If it already has data in it, you're not allowed to write to it. Further complicating things is that you can't erase an individual block. You can only erase large groups of blocks. We call them erase blocks. Obvious name. And it turns out that an erase block will have many of these data cells in it. So a read block, or read-write block might be 4 or 8 kilobytes, but an erase block is often going to be several megabytes, just because it's more efficient to build the machinery that way. So if you have a solid-state drive that has empty blocks, okay, they actually store no data right now, then the SSD can write to that block. It's going to be on the order of tens to hundreds of microseconds, probably tens of microseconds. And it's going to be fast, and you'll be super happy you upgraded to an SSD. You'll be like, wow, that hard disk was slow. But if you have a situation where the solid-state drive is out of empty blocks, then you're sad because now you have to go in and erase things so that you can get more empty blocks to write into. So again, to just sort of fill in the picture a little bit, we have all these blocks and we don't address them directly. Just like on spinning magnetic disks, we don't address them directly anymore. The whole cylinder head sector addressing mechanism is kind of defunct now because of things like zones on platters and so forth. So we have this logical block addressing, which starts at block 0 and goes all the way up to the maximum block index. And the hardware maps that to a physical place where it's stored. And the same thing is true on solid-state drive. They have this thing called a flash translation layer. And so it takes the logical block number and maps it to a specific read-write cell that holds the data for that logical block. Okay? And so you have this so recall system uses logical block addressing. That's more for the OS class. This is not something we really talk about in here. So files are into the SSD. Has to store the data in empty cells. And so we have a couple of interesting consequences of this. If you edit a file, and I mean, any programmer worth their salt kind of develops this nervous tick of saving files all the time. I don't know if you guys do that yet. You will. I've lost lots of code when I didn't save frequently, and I don't like that anymore. So I go ahead and save a lot. And every time you have that file and you modify it and you save it to the solid-state drive, it can't rewrite it to the same cell. So what happens is when you're doing these edits, the solid-state drive is saying, okay, this cell is no longer in use, and now I'm going to store it over here. And it stores the updated version. So block 2 of file F1. So F1.1, F1.2. F1.2 is going to be modified. So it marks that as no longer available. So the contents are old. They can be reclaimed. Nobody's using them. And it stores the new version of F1.2 somewhere else. Okay? And the flash translation layer has to be updated because now the logical block number hasn't changed. But the mapping has to change because the physical cell that it's stored in has now moved. Everybody got that? This is what happens every time you hit Control S or you auto-save your spreadsheet in Excel or whatever. It's doing this kind of junk underneath the hood. Okay, now obviously over time you end up with a lot of cells that are marked as old and they still have junk in them. So we have to reclaim them somehow. And so basically we have to start figuring out what blocks to erase. And if you have a situation where the entire erase block is now old, that's awesome. That one's easy. In fact, I constructed that example just to show you. So we erase this one, and boom, suddenly now I have a whole bunch more cells that I can use. Okay. So I take all of them and I wave the magic wand at them, and they all get erased at once, and now I can use them. And so here I write to F2.1 again, and you can see, no, actually I wrote to F1.2. I guess I'm dyslexic. So F2.1 gets changed a third time, and so let me see, the old F2.1, was in the first erase block, so that went away. The second one gets marked as old, and then the third one gets stored in the new erase block. So that's nice. That one's a fast and easy one. Okay, this is slower. So now you're talking probably like at the hundreds of microseconds range because erasing an erase block is a little bit slow, but it works. But sometimes you have a situation like this where basically the solid-state drive is like, I need more cells. I'm getting scared. I need to start getting some space for writes. And there are no erase blocks that have only dead cells. So now we have to do something about it. Let's say that the solid-state drive decided that it wanted to reclaim the third erase block, but we still have data in there. So what can it do? Just relocate those things, right? So we can copy those things out, and then we can go ahead and erase that block. And again, the flash translation layer is updated to say, hey, this is where these things are stored. I had to move them so I could get the erase block back. And so you can see that before we had 3 cells available, and then we relocated these things, and now we have 5 cells available. Okay, so we have taken a step forward by doing this relocation thing, but it's kind of an interesting consequence that has this disturbing implication. that sometimes when I'm doing a write, I do a single write, and I may have to, the solid-state drive internally has to do a bunch of other writes just to complete my one write that I wanted to complete. So we call that write amplification. And so what happens is if this space is not managed properly, you start to see the solid-state drive get slower and slower and slower as it gets fuller and fuller and has more of this kind of messy situation with erase blocks that aren't entirely, empty, and situations like that it has to deal with. You run into this kind of problem. Okay? Questions? All right, so that's a little bit of detail there. Now, just to complicate this a little bit more, these cells do wear out. You can erase them like 10,000 times or 50,000 times. I can't remember exactly how many cycles they can take, but they kind of design the drives in the hopes that they will actually last about 5 years if you're just totally beating the crap out of them. And if you're ever curious about this, you can actually get on the internet and look for, there's people who have been doing tests of just setting up machines and writing to solid-state drives over and over and over again. Like they've put through multiple terabytes worth of writes to solid-state drives just to see how well they hold up. And so they have like a battery. There was one test I saw where they had a battery of like 8 or 10 solid-state drives, and the higher-end ones are fine. They're like, whatever. And the lower-end ones are like starting to burn out and fail in various ways. So it's kind of an interesting thing to read about. But anyway, so the solid-state drive has to think about that kind of stuff as well. But here's the question. How does the drive know that a cell is no longer in use by the system? Because remember, this is a device that's being used by the file system. So how does it know that a cell's contents is no longer needed? What obvious thing tells us that it's no longer needed? How about I write to that logical block? If I write to the logical block, I know I don't need the old version of that block. And so the cell that the old version was in is now available to be reclaimed. This is kind of a sucky way to find out that something is not needed anymore. Everybody see that? Because we run into this big problem as time goes on. Because remember that the operating system wants to touch the disk as little as possible. And so if I delete a file, what do I actually touch? I touch the directory entry. I may touch other bookkeeping stuff to say the space is now available. But I don't touch the contents of the file at all unless I'm doing secure deletes and that kind of stuff. But even if I'm doing secure deletes on an SSD, it's like, yeah, whatever, good luck, because secure deletes are just going to go into a different cell. The old cell's contents are still there. Okay? So the consequence of this is that the solid-state drive will have a perception of what cells need to be preserved, what cells have data in them, and it doesn't match what the operating system thinks are cells that have data that needs to be preserved. Like you see here, F3 is deleted from the solid-state drive. So we have F3.2, 3.3, 3.1 prime, 3.4 prime. And the solid-state drive doesn't know that it doesn't need to preserve those things anymore. It just sees like the directory entry get changed, and it's like, okay, I'm just going to store the data. It doesn't know the file system format. So now we have a situation where if we decided to erase the second bank, the solid-state drive will now think it needs to move 3 cells instead of just 1, which is the actual truth. Okay, so I erase the second bank, and it's like, oh, I've got to relocate 2.2 and 3.2 and 3.3. But the OS knows I don't care about 3.2 and 3.3 anymore. So we have this mismatch in the knowledge between the OS and the device. So this is where trim comes into the picture. Trim is basically a way that the OS can tell the solid-state drive, without actually performing a write, that it is done with particular logical blocks. So it issues a trim command and says, hey, device, I am now done with all of these logical blocks. You can mark them as old, but you don't have to create a new version anywhere. And then that allows the solid-state drive to be a lot more clever about how it manages these erase blocks. So like I say here, what you could do instead, if the OS supports solid-state drives and trim, is it can go in and mark all of those parts of file 3 as not in use anymore. And now the SSD can be much more clever about this. If it needs to delete the second erase block now, it can just move F2.2, for example, to the first erase block. And then just write out the whole thing. It doesn't care about F3 anymore. Okay? So basically, this allows the solid-state drive to be a lot more clever. Are there any questions? This is why if you have trim disabled on a solid-state drive and over time your writes get really slow, this is the reason why it gets slow, because you have this write amplification that occurs more and more. The device thinks that blocks are in use that the system does not. And so that's why most of these systems have some kind of trim command. Just a few details to point out is that it used to be that trim was like stop the world garbage collection. You had to not do anything else when you issue trim. Okay? So you actually had to wait till, you had queued commands, which were pipelined, and you had trim, which had to be done all separate. And so thankfully, that's been fixed. Yeah, so that's what I was basically saying before. So an updated specification came out and fixed this, and so you'll see this more and more frequently, that trim will be a queued command that can be fit in with everything else that's going on with the drive. Okay, so let me see, anything else? Yeah, so the other thing is that not all OSs support trim yet, but the thing is that it's really common now. Solid-state drives are becoming really ubiquitous, so this is really becoming a non-issue now. Pretty much every major operating system supports it, and quite well. So this is kind of an issue that's thankfully gone away. Any questions? All right, well, now you know a little bit more about solid-state drives. Since they are so common, it's probably a really good idea to have some knowledge of them. But anyway, that's all I wanted to talk about with that. And Wednesday we'll do the final exam review, and then Friday have fun or something. So.